All right, for these problems, I want to give you guys the full solution, but remember that of these three problems, the first and the third are the longer problems. The 25-minute problems they give you if it was the AP test, where you would have then 5 minutes to upload. The second problem is one of the shorter problems, the 10-minute problems with the 5 minutes to upload. Now you can bleed a little bit into that 5 minutes to keep working on the problem if you need to, but don't overdo it so that you have problems uploading. Because I'm not sure exactly how they're going to do it. My guess, and this is only a guess, so don't count on it, is that if you're a couple minutes late, they're not going to hold it against you because, you know, they don't want to have to deal with people who had problems just because they couldn't upload. But since not all of you are, only I think 7 or 8, no, like I think 11 people are taking it, so it should be okay. All right, so problem number 1, I wanted you to look at the problems a little bit beforehand. So they'll almost always have a diagram similar to what we have on the test, where it shows you a number of things. Read through the written information. But in the thing it says he's moving at a constant speed of 1.2 meters per second. Whenever you see constant speed, you should, especially if it's in linear terms, you should think zero acceleration. But there's also a coefficient given there, so that should remind you, oh yeah, there's probably going to be friction. It gives you distances and speeds and masses, so you know a lot of this older physics is what you're going to have to do. So what we're going to do is we're going to start with that free body diagram. And then whenever you're doing the free body diagram, you just start with the object. So in this case, it's the crate. If it was asking about the person or the elevator door, you would start with those things. But make sure it says the crate, so start with the crate. And then I'm going to start labeling the forces acting on it. So we know always there's the weight of the object, the earth pulling downwards. And I didn't feel like just typing it out here, but you would put in parentheses the earth on the crate. Then we also know, because it's on the floor and it's not falling through the floor, there's a normal force upwards. And because it is not going through the floor, you could put a little dash through each of those lines showing that they were equal. Then there's a frictional force backwards. We know it's backwards because he's pushing it to the right, and then the frictional force is always going to oppose that motion. So if it's moving to the right, the frictional force is to the left as long as it's sliding. And then, because the person's pushing, there's his force to the right. Because we know it's not accelerating, if we turn this free body diagram into equations, Newton's second law is just kind of writing all the forces in the x direction minus all the forces up minus all the forces down, and all the forces to the right minus all the forces to the left, and setting that equal to mass times acceleration. In this case, the acceleration is 0, both horizontally and vertically, so we know that the person is pushing with a force equal to friction, and we know that the normal force equals the weight. And so that allows us to solve, because we go to part B, because we know that the normal force is equal to the weight, and the weight's one of those things that we can calculate very easily. That's going to be our 294 newtons. If you use G was 10, you would get about the same answer. You get 300 newtons. And for the AP test, they're fine with that. If you just use G equals 10, you won't lose any points anywhere. Then it says the vertical forces, and with friction, you find the force the person's pushing it. So the idea here is, because it's going at a constant speed, the push to the right equals the friction force to the left. And we know the definition of friction is just mu times the normal force. We found the normal force, so that push that person has to do is 58.8 newtons. So if you pushed with less than 58.8 newtons, it would start having a negative acceleration, which means it would slow down since it was moving to the right. If you pushed with more than 58.8 newtons, you would start to accelerate to the right, a positive acceleration in this case. So for part C, it asks, how hard does the person have to push on that crate? So we know if you push with greater than 58.8 newtons, it's going to start accelerating. But first we want to figure out, does it actually need to accelerate? Because maybe it's just going fast enough it'll go on its own. So I'm going to figure out how fast it goes if there's no acceleration. And the distance it travels with no acceleration is really easy. It's just 1.2 meters per second times 9 seconds, because the 4 seconds before the elevator door opens and the 5 seconds after. And then if you multiply that, you get 10.8 meters. So now we know that in that extra 5 seconds, you need to go an extra 5.2 meters. So that 5.2 meters is going to be that distance that you need. So knowing that that is the piece here, I can say that 1/2 AT squared. So that 5.2 meters is 1/2 acceleration times 5 seconds squared. And I get acceleration as 4.16 meters per second squared. You could also do this a number of different ways. You could figure out how far it went during the first 4 seconds, and then to use the full kinematics equation. The delta x is v0t plus 1/2 AT squared, and you would solve and get the same thing. You could also just graph it, and I'll talk about that in just a second to show where that 4.16 meters per second squared would come from. All right. So if we look at Newton's second law, we know that the net force in the x direction is going to be the person pushing minus friction equals ma. So if I solve that, I get that the person pushing equals the frictional force plus ma. M is 30 kilograms, a is 0.416 meters per second squared. So I have to add up those two forces. So it'd be about 71.3 newtons, or you can even round it down to 71 newtons. Because it's not as many there. So if you push with, so if the person pushes with that much force, they'll get to the elevator door right as it's starting to close. So you would hopefully be able to make it in, or you'd just be just short, and then you'd be really sad because you don't have any time to decelerate, so you'd slam into the elevator doors. So we'll see. They weren't as specific on there. All right, so now is the thing that you definitely need to make sure you're used to is the idea of the graphs. And so for the graphs, instead of just digitizing them, what I've decided to do is just use my document camera and show them a little bit. So here are the 3 graphs. I printed them out on my own. So I'll start in the order that they did. So I'm going to make a mark here at 0.5, and then my units are meters per second squared. So I have this value here. Now for the first 4 seconds, it's not accelerating, so I would explicitly draw in a line here that it's 0. And then at that point, it would jump up to 0.416 meters per second squared for that entire remaining time across there. Now you don't need to connect the lines up and down, but if you want to be explicit about it, you can kind of show that there. Okay, now the velocity is a little bit easier. We need to figure out, where that value is. We know it's going at, let me just go 0.5, 1, so 0.5, 1. Actually, I want to go, let's do just 1, 2, 3, because I know, did the calculations a little bit myself here to figure out what it was going to do. So at the beginning, the first 4 seconds, it's going at 1.2 meters per second. It's a constant speed, so I would draw that as a straight line there. Then, once you get to the end there, we know we're going to be speeding up. So it's going to be going at, it's increasing at 0.416. So it increases by 2.08. So it's up at about 3.3 or 3.28. So we know at the end, we're a little bit above 3 here. So this point here, it's going to get up to that value. And it's increasing. The slope of that line is our acceleration. I could also figure out that this part here, the area of that, equals 5.2 meters. Because the area is that. So you could actually put that together. As long as you knew the base and the time, the base, which is the time, and you know the area, you could find the height, and that would give you the time, and that would also let you, or the final velocity, and that would let you figure out the acceleration if you wanted to. So that's just one of those things that you could, that's another way you could solve the problem. But here, we know we end at 16 meters. We know at the very end we're going to be at that point. As it's going through there, for the first 4 seconds, we go a certain distance here. So I'm going to go, let's see, 4, 8, 12, 16. So it goes for about 4.8 meters. So it's going at a constant speed. So that means it's a line with a constant slope. So during those first 4 seconds. Then, because it doesn't travel at that speed, it actually speeds up. It's going to be a parabola, and it's going to end up curving up to that point. So you have to make sure there's a difference here between those points where it's a straight line and where it's a curve. All right, so that'll be that's problem one. This took a little longer than I intended, so I'm going to split up each of these solutions into its own video.